Now, I thought tonight it might be fun to travel to Titan as tourists and go there for a holiday and see what we can learn about it from the point of a tourist. Now, Titan is the largest moon of Saturn, and I actually think it might be the most fascinating place in our solar system. It's the only place, apart from Earth, that has seas, lakes and rivers on its surface. Now, it's way too cold for liquid water, so there's the liquid methane. As well as that, the chemistry and the atmosphere of Titan are very similar to the ancient chemistry and atmosphere of the Earth, so it makes it a perfect natural laboratory for us to study Earth's early atmosphere before life developed. And as well as all that, it has a hidden ocean. So under the surface there's a deep saltwater ocean. It's a global ocean, which may have as much water as maybe 10 times as much as the Earth. All the Earth's oceans put together. So that's a lot of water, and that would make it the largest ocean in the solar system. So we'll go there in a moment and see what we can learn, but also what we can do there for fun. So I'll start off with a little bit more of an introduction to Titan, a few stats and a bit of information about it. And back one step. And then we'll see how we can get to Titan and just how far away it is. We'll land on the surface and do a bit of exploration and see what we can discover there. Now, when I was writing the talk, I actually used artificial intelligence for a couple of the images, which worked well most of the time with a bit of playing around, but there were a couple of failures, and one was I asked for a spaceship that can take 10 people from Earth to Saturn in 5 months. So it gave me a spaceship and shoved Earth up the back of it. I'm not sure if it thought we were taking Earth to Saturn or if it was telling me what I could do with the Earth. So that was one failure. Right, let's have a look. First up, what is Titan? So if you get your telescope out and you find Saturn, you'll see the beautiful rings, as we all see with Saturn. But you'll also, if you're lucky, see an orange dot just a little bit away from Saturn, and that will be Titan. As I mentioned before, Titan is Saturn's largest moon, and it's the second largest in the solar system after Jupiter's Ganymede. It's actually only 98% of the size of Ganymede. I shouldn't say only, it is 98% the size of Ganymede, so it's a very close second to being almost the largest moon. Christian Huygens discovered Titan in 1655, and he named it Luna Saturni, and that is Latin for Saturn's moon. So of course it was the first moon seen, so Saturn's moon, Earth's moon. But amazingly enough, now we know there's 146 moons surrounding Saturn. That was updated 8th of June, just a little while ago. At the start of the year in February, there was about 83 moons on the list, so you can see the numbers going up as more and more are discovered. Most of those are kind of asteroidy, kind of small rocky things, but there are a number of more moonly moons. So moonly moons, I guess I don't know if that's a real word, but what's that? Yeah, well, no, that's a me term. The moonly moons. So there's a few moonly moons there, which, oh, no, I must have forgotten one. What have I forgotten? Hang on, something's come up here. Okay. We don't want that one there. Okay, that was not a moon. So there are a number of moons that are actually round and spherical, like you'd expect a moon to be. But of course, we're concentrating on Titan, so let's have a look at Titan here. This picture shows Saturn and Titan and Earth and the Moon all to scale with the sizes and the distances between the planets and the moons. The average distance between Saturn and Titan is 1.2 million kilometres, and you compare that to Earth-Moon distance, 384,000 kilometres. So Titan's about 3 times as far away from Saturn as our Moon is from the Earth. Titan takes almost 16 Earth days to orbit Saturn once, compared to our Moon's 27 days. So for every orbit that the Moon does around the Earth, Titan actually does about 2 orbits around Saturn. And Titan's also tidally locked towards Saturn, so the same face is always pointing towards Saturn as it orbits around. And that means that a day on Titan, I should say, is also about 16 Earth days. It's probably better to think of that as 8 Earth days of darkness and 8 Earth days of sunlight, so very long nights. Now, a year in the Saturn system is nearly 30 Earth years. And because Saturn and its system are tilted to the ecliptic, just like Earth is, Titan's and Saturn are about 27 degrees to the ecliptic. So that system will also have seasons. Each season will be about 7.5 years. So that means on Titan, it'll have a 7.5 Earth year, summer, winter, spring and autumn. So not only very long days and long nights, but very long winters and long summers. Not much difference though between the summer and the winter on Titan. As we'll see, it's still very cold. So how do we get to Titan and where is it? Well, you'll know, or you may know, that Earth orbits the Sun at 150 million kilometres, and then we call that 1 astronomical unit, or 1 AU. Saturn is about 9 to 10 AU away from the Sun. So it's at 10 at its furthest distance and 9 at its closest, because its orbit is slightly elliptical, so not quite circular. And so that means that the closest approach that Earth and Saturn can be is about 1.2 billion kilometres, and that's just over a little bit over an hour of light travel time. So if you were talking to someone at Saturn from the Earth, it would take about 2.25 hours from the time that you sent your message to the time you received something back if they replied straight away. So it is a long way from the Earth, 66 light minutes. That's a fairly big distance. Now this thing over here on the right is the Cassini probe, and attached to it is the Huygens lander. You can actually see that gold thing is actually the heat shield for the lander. Now this was launched from Earth in 1997, and after a 7-year trip going around the Sun a couple of times and getting some boosts off various planets, it arrived at Saturn 7 years later in 2004. But tonight we haven't got 7 years to sit here, so we'll have to sit here for 5 months, and we'll see if we can get there. Well, pretend we've got a spaceship that can travel that distance in 5 months in a straight line, maybe 1.25 billion kilometres. Now to do that, we'd need a spaceship that can fly at, or can travel at 95 kilometres per second. That would be fast enough to get to our moon in just over an hour. So we'll take off when Earth is here and Saturn is over here. 5 months later, Earth will be over the other side, around the other side of the Sun, and Saturn will have moved a little bit there. And all going well, we should rendezvous with Saturn in 5 months. So we're going to leave the Earth behind, not take it with us. And 5 months later, we'll arrive at the Saturn system. The first thing you'll notice, if we fly to the system and come around to the dark side of Titan, so the Sun's in the other direction, you'll notice maybe, if we're lucky, a little glint off the northern hemisphere of Titan. Now that image was taken by the Cassini probe in 2009, and that was the first hint of liquid water on Titan's northern hemisphere. Liquid on the surface, I should say, of Titan's northern hemisphere. Liquid had been identified in the south earlier, but this was very exciting as it was the first obvious clue as to liquid on the surface in the northern hemisphere. The atmosphere of Titan is very thick, so this is actually done with infrared light, as we can't see through the thick haze with normal visible light. So if we head round to the sunny side now and have a look at Titan, we can see that we can't see much at all. It's extremely dense, the atmosphere, so we'll need infrared instruments to be able to see through. And this is an image taken using infrared, looking through the haze at the surface of Titan. Around the equator here, these dark areas are sand dunes, so these are deserts around most of the equator of Titan. And up the northern pole here, the large areas are seas of liquid methane, and there are hundreds of smaller methane lakes there as well. So if we zoom into the seas and lakes on the north, we'll just have a quick look and see what we've got there. There are 3 seas, Punga Mare, Kraken Mare and Ligeia Mare. So Mare means sea, and each of these are named after mythical sea creatures on Earth. Punga is the Maori word, and it's the ancestor of all the sharks, rays and lizards, and all the deformed, ugly things. Ligeia is a siren from the Greek myth, and kraken, we've all heard of kraken. So kraken mare, punga mare, and Ligeia mare. To give you an idea of the size, that's New Zealand to scale next to them. New Zealand is about 270,000 square kilometres in surface area. Kraken mare about 490,000 square kilometres of surface area. So kraken mare is about twice the surface area of New Zealand. So you can see it's fairly large sea. And that glint that we saw off the surface or off the northern region of Titan is thought to have come from a south shore of Kraken mare. It's a little bit hard to tell exactly where a glint is coming from through a hazy atmosphere, exactly where it would be coming from, but it was identified as probably a southern shore of Kraken mare. Before the Huygens probe landed on Titan, the scientists weren't sure whether the whole surface might have been covered in liquid methane, but it turned out that the seas and lakes are really at the north and south poles, are limited to the north and south poles generally. So we're going to cheat a little bit now, and we'll use a Google map of a Google global map of Titan, which you can actually find on Google Maps if you look in the right places. I can show you later on how to do that. So we will just rotate Titan around to the other side and have a look over here. What we have on the left here, that's Adiri, which is a slightly raised, lighter area. And over on the right, Shangri-La, that's the Shangri-La sand sea. It's a large desert. All that darker area is the sandy parts. Not normal sand like we have on Earth, but we'll have a look later and see what that sand is. And here's a nice place I think we can land. It's conveniently where the Huygens probe landed, so we can just land there and use the images from the Huygens probe and pretend that we're landing on the surface of Titan. So I'll just show a bit of a short part of a video from NASA, just showing the initial deployment of the Huygens probe from the Cassini, as it entered the atmosphere of Titan. So here we are with this starts off with an animation. Oopsie, what do we got here? Back again. So the Huygens probe is, I'm not sure if that's my computer there. No, we're all good. So this is actual imagery from the Huygens probe as it just entered the atmosphere, or entered the hazy part of the atmosphere of Titan. So you can just start to see some landforms appearing here. But I'll jump now to, I will jump in a minute, to another video which will show some rendering of the images taken from the Huygens probe in a format that looks more like if we were looking at a normal window. These are taken through a fairly fishbowl kind of lens. So the images we'll have in a minute, let's hope we can get that to work. We seem to have a slight issue there. Might just have to jump out of that and come back in. Interesting. Slight technical difficulties here. I think we've had a look up here. We have a problem.
Just kill PowerPoint.
Yeah.
What's the 2.5-hour descent?
Yeah, so you can just sit back and just dream about descending for 2.5 hours. PowerPoint doesn't want to disappear either. Okay, we may be doing... Who's our technical person here, Steve? You may be able to get us sorted again. Apple. I'll put that on the shopping list, eh? It's all right, there's still 2 hours and 20 minutes left. Yeah, so that was the haze, and now we're looking at a galaxy far, far away. Probably if we go to that one there, we can skip the offending video. Oh, it's doing the screen thing, so I wonder if we need the Windows P. Shall I reboot the computer?
Maybe. Yeah, I'm not getting any signal there.
Yeah, okay, let's just quickly do that, eh? Windows 11 should be fairly quick to reboot.
It froze you guys.
So I think it's still trying to read the screen there, isn't it? Oh, what's it doing?
Technical difficulties?
Here we go, we'll reboot that one. Yeah, I think it's just one of those computers trying to connect to each other kind of thing. Here we go, looking good. Here we go, up and running here. Right, we're going here. Must be a connection down here, I think, that we've...
Windows P.
Yes, Windows P. And what are we doing here? Extend. Oh, there we go. Extend. Yep.
It's a bit twitchy, that touchpad, eh?
Yeah. No. I'll get rid of presenter view, eh? That might be making it more. I see you're making it struggle more, I think. It's trying to connect, I think, but it's just struggling. Right, so that's up on the screen here, so just get that little connection there.
Do you want to just try directly into here?
Could do, eh?
These things go so smooth.
They do, don't they? That's right, it's only halfway down to the surface, so you're not missing anything. Yeah, yeah.
Still another hour or so to go, right?
Yeah. I think they serve tea and coffee. So it's coming out of here, okay. Oh, there we go.
Oh, there we go.
Okay,
Yes.
so I'll go through. Okay, I think we're good to go. So here we are now, back into the atmosphere again. This is a render of images from Huygens by an artist, René Pascal, who designed a video and some images to give us an idea of what it might look like if we're actually flying through, landing on Titan. And so the first thing I notice is the blue sky, just like we see on Earth, which is probably a bit of a surprise. That's blue for the same reasons that the sky is blue on Earth. It's called Rayleigh scattering, and the blue light is scattered more than the other colours. So the blue light gets scattered around and reflected back to us from different directions, giving the blue sky. And that'll be why the nitrogen in the atmosphere of Titan and the oxygen and nitrogen on the Earth's atmosphere give us the same effect. So as we continue further down, eventually we'll come through the haze and we'll start seeing some of the landforms. We have to get down below about 70, 50 kilometres to get through the haze to the clearer atmosphere. So at the moment, we're just looking out the window at a probe that's just heading down through the haze. We'll come out through the bottom of the haze in a moment. But as that's happening there, I'll just show you a couple of pictures over here, which you can start to see the channels here of, so these are dry riverbeds where methane used to flow into this area, which is thought to be a dried lake bed. So probably these channels were formed by flash flooding and heavy rainstorms in the past. So we'll whip over and just have a quick closer look at these images here. So this is the area we're going to actually land at about here. So this is the dark sandy deserts here. And you can see those landforms there. Now it's quite dark on Titan. Because Saturn is 10 times as far away from the Sun as the Earth is, only 1% of the light reaches Saturn as compared to the Earth. So it's 1/10 of a tenth. And through that thick atmosphere, only 10% of that makes it through. So the amount of sunlight that gets through to Titan is 0.1% of the amount of sunlight that we have on a hot sunny day on the Earth. So it's fairly dark, but not too dark to see. And we'll jump back to the other NASA video and just have a look at the last parts of the descent. These images were taken by Huygens, and these are 360-degree images, so I've stretched them out a bit just so that you can get a better idea of what it might actually look like. And so for the last 15 kilometres down to 400 metres above the ground, that's our landing spot there. So as we come into land at that spot there, we'll just head down towards the ground there, and we'll see as we come close to the ground, we'll see a lot of rocks around the landing area. Now these are actually ice, so it's so cold on Titan that water gets frozen as cold as granite. So the rocks there are actually made of ice. Now these are rounded, which shows that there was liquid flowing there, liquid methane, which would have rounded the rocks just as much, just like they get rounded on Earth. Well, the real rocks on Earth get rounded by the same processes. They look quite big, but really if you compare them to a footprint on our moon, so the same perspective, it shows that they're actually quite small, maybe 10 to 20 centimetres, these particular ones. And they look big because the Huygens probe was only about that high and the camera was quite low down. Yeah.
Is it actually that bright, or is it?
So it did have a light, so you can kind of see the bright light from the light of the probe, so it kind of was shining a bit of a light that direction. It's slightly artificially coloured as well, so the colours might have been brought out a bit more to make it easier to see. So now that we've landed on the surface, finally, that was almost 2.5 hours, so it did feel like a rather long time. So that made it more realistic. So we're on the surface, and now we'll go and explore the surface and see what we can find and what we might be able to discover and what we can do there as well. The first thing we would have noticed as we were coming through the atmosphere is that it was mainly nitrogen, between 95 and 98% nitrogen, with a bit of methane, 2 to 5%, a little bit of hydrogen gas, and hundreds of other smaller molecules as well mixed into the atmosphere, but small amounts of those other molecules. It's interesting to compare that with the Earth, which is also mainly nitrogen. So our atmosphere is about 78% nitrogen, oxygen about 21%. Carbon dioxide, 0.04%, which has increased from 1960, where it was about 0.03%. So there's been a rather drastic increase in carbon dioxide. But the main thing is the nitrogen is the main component of each of the atmospheres. But what's even more interesting is comparing it with Earth's ancient atmosphere. Now, in the distant past, the atmosphere was mainly made of nitrogen and carbon dioxide, and of course no oxygen, with no life at the early times. For the first 2 billion years of Earth's history, nitrogen and carbon dioxide at various different mixes. I don't think the exact amounts are known, but by about 1 billion years, nitrogen would have been a major component of our atmosphere. And so this is why I said before that Titan's atmosphere now is a perfect natural laboratory for us to study what the atmosphere might have been like and the chemistry occurring on in Earth's atmosphere back in the very early stages of Earth's history. So looking again at the atmosphere here, up at the top here, have a look at that methane fluorescence. So that is methane gas in the atmosphere fluorescing, taken at a infrared wavelength. The fluorescing methane was up to 700 kilometres above the surface, so that shows that the atmosphere of Titan is about at least 700 kilometres high. So methane up to here and some nitrogen as well, but that absolutely dwarfs the Earth's atmosphere here, which we think of as finishing at about 100 kilometres. So if you think of our atmosphere finishing at 100 kilometres, and then on Titan another 600 kilometres above that, it just shows how small our atmosphere is compared to Titan. That light blue line there is roughly where our ozone layer would be. And the little images there's Mount Everest, cirrus clouds there, and various other clouds. So you can see that Titan's atmosphere is huge compared to ours. That's where the space station would be orbiting, about 400 kilometres above the Earth roughly, and that would be well within the atmosphere of Titan if it was on Titan. So that's pretty incredible, I think, just how much of the atmosphere there is. That's the orange haze down here, and there's various layers of the atmosphere. They kind of change during seasons, so the height of the various different layers changes here and there, and there are some detached layers further up as well, which you might see in some photos of Titan. And although this slide is quite a busy one, it's really interesting just to have a look and see what's happening in the atmosphere. So I mentioned that methane and nitrogen are two main molecules in the atmosphere. So way up high, these get broken down by energy from photons from the sun, ultraviolet photons, as well as energetic particles from around Saturn. It breaks these molecules up and they reform to form other molecules. Benzene is one of them that forms, the benzene ring, so there's a lot of benzene in this haze. And the benzene rings join together to form what's called polycyclic aromatic hydrocarbons, or PAHs. These are big groups of big molecules that join together further down to form aerosols, and these aerosols fall to the ground almost like a snow. So these molecules are giving us the orangey colour of the haze and the orangey colour of the ground as well. There are a lot of other, just flip through there, a lot of other molecules are formed as well, so including hydrogen, ethane, acetylene, benzene as we saw before, hydrogen cyanide and cyanogen, so there's some very interesting molecules there, as well as a lot more. So once we land on the surface, we'll find, as I mentioned before, that it's very cold, minus 179 degrees Celsius. That's probably a hot day or a heat wave on Titan. It actually gets a little bit lower than that, so you'd never get warmer than minus 179 degrees. So we're lucky, we've just landed in a nice warm spot. And if you compare that to liquid nitrogen on Earth, which is about minus 195 degrees, and we stick a flower or a plant into liquid nitrogen, you may know from high school science that if you take it out and then shatter, it'll just shatter like glass. So that's the kind of cold temperatures we're looking at as we've landed on Titan's surface here. The pressure is a nice 1.45, almost 1.5 times the air pressure on Earth, which is good. It means we wouldn't have to wear a pressure suit. We just need a space suit for the cold and to breathe, of course. And that would be not too different to being about 5 metres underwater, so we could handle that quite nicely. The gravity is about 1/7 of the Earth's. That's 0.138 g. So the moon is about 1/6, so it's a little bit less gravity than Earth's moon. So when you see the astronauts bouncing around on the moon, on our moon in pictures, then you'll be able to bounce around a little bit higher on Titan. And the air density is about 4.5 times that of Earth, so fairly dense atmosphere as well. And we'll see how the air density and the gravity can allow us to do a few fun things later on. And I mentioned before, it's very dim there, about 0.1% of the brightness on Earth. So now we'll go and actually have a look at some bits and pieces on the surface, and we'll start with the equatorial deserts. So if we start over at our landing place here, go over Adiri, over to the Ballot Sand Sea, which is a desert, equatorial desert. This image on the right here is a radar image taken by Cassini. And you can see the lines there, which are sand dunes. Now, these are very similar to sand dunes on Earth, probably in various places on Earth, about 100 metres high with a good separation between them. And if we compare that with the Namib Sand Sea on the Earth, we can get a good idea of what they might actually look like on Titan. So that's the Namib Sand Sea in Namibia, taken by a radar image of it, compared to the radar image from Titan. And that's a photo of the sand dunes here. So we can assume that these probably look much the same. And here is a photo of a sand dune in the Namib Sand Sea, taken from the ground. And over here is artwork by NASA showing what they thought the sand dunes might look like in the deserts of Titan. So you can see very similar to Earth. One difference, though, is that these are probably coffee coloured. So it'd be a kind of a dark brown coffee coloured sand dune. Now there's more to these sand dunes than meets the eye, so we'll have a look at what's going on here. It's thought that these are possibly electrified. Now that's a bit dramatic. Probably static electricity is what's going on here. And the reason they may be electrified statically, much the same as this cat here, if it's sitting in a box of polystyrene balls. So static electricity from the polystyrene balls means they'd stick together and stick to us. Much the same sort of thing is probably happening with the sand dunes in the deserts here. The reason this is thought to be the case is that the sand dunes on Titan are facing the wrong direction. And when I say the wrong direction, the prevailing winds on Titan go a certain way, and they're fairly light winds, and they should be blowing the sand dunes to be pointing a certain direction, but the sand dunes are pointing the wrong direction. It's thought that the stronger winds, which occasionally blow around Titan the other way, may be forming the sand dunes, and so the weaker prevailing winds are not able to force them back the other way. And that could be the case if they held together with static electricity, holding the grains together. Seems to be the perfect answer. And scientists have actually taken molecules, or made molecules, that would be similar to the ones on Titan and found that they do in fact become statically charged. So it does seem to be a good answer to the problem of what's going on there. So really what that means is that this sand is actually from the sky, so it's not sand like on Earth, it's the molecules coming from the sky. So essentially we have electric snow forming electric sand dunes. So now we'll head over to the mountains and see what we can see over there. So we'll head from where we were here, back past our landing site, over the Shangri-La sand seas, over to this area called Xanadu. Xanadu is a bright raised area, probably about the size of Australia. And on Xanadu is, or in Xanadu, is this area called the Mithrim Montes. This is a triple mountain range, so there are 3 mountain ranges here, with the highest being about 3,300 metres or 3.3 kilometres. So that's the highest mountain on Titan that we've found here. The mountain ranges are parallel, and for a sensible reason. It's thought that they've probably been folded together with tectonic processes, so the ice has kind of been pushed up, the ice crust pushed up, forming this triple range of mountains. You can see the size, about 50 kilometres roughly between each of the mountain ranges. Now what that might look like, maybe it might look something like this. So here's a bit of an idea. If we were maybe looking down the valley here, we may see something like this. So that gives you just something to kind of visualise what it might look like if you were there. Now, I mentioned before about the atmosphere and the gravity. And you may have tried that. I don't know if anyone's tried it. That's something I'll never do. I don't think I'd want to be that, live that dangerously. So over there on Earth, of course, where we have someone using a wingsuit to fly, and they'll have to head down towards the ground. But on Titan, because the gravity is only about 1/7 of that on the Earth, and the atmosphere is about 4.5 times as dense, there'll be a lot more lift and a lot less gravity pushing you down, so you may be able to just flap your wings and actually go up and carry on flying. Maybe you need a bit more of a wingsuit, but it wouldn't be too hard to actually fly around with the right gear on Titan. So it's a fun thing you could do. In fact, Titan, because it is such an easy place to fly, there's a mission called the Dragonfly mission, which is launching in 2027. And that'll be arriving on Titan about the mid-2030s. It's an octocopter, so it's about the size of a car, maybe 3 meters long, and it has 8 blades. And it will fly very easily on Titan because of those conditions, and that's going to be the main transport as they look around the surface and see what they can find. So we've seen the deserts. It's time now to head up to those northern seas that we looked at the start. So we'll take off from the Mithrin Mountains here and we'll fly right up over Titan, over the North Pole, and have a look at these northern seas. The first one we'll have a look at is Ligeia Mare. And this is a radar image of Ligeia Mare, and just comparing it to New Zealand's North Island gives you a bit of an idea of how big that is. So it's a fairly big lake, or a fairly big sea. It's the second largest one. Now this sea, Ligeia Mare, consists of maybe about 80% liquid methane and a little bit of liquid ethane, maybe about 11% of ethane. Also has a bit of nitrogen in it as well, maybe up to 17%. Now the amount of ethane is a bit lower than Kraken Mare to the south, and it's thought that the methane rains either wash a lot of that down into Kraken Mare, which has more ethane in it, so it kind of keeps this one clearer. It's a bit like salt water and fresh water, so if you had a saltwater lake and you had a lot of freshwater rain, it would wash that salt water down into other areas. So that's possibly what's happening there. The other theory is that it could possibly be absorbed at the bottom of the sea by the ice there. The sea itself is probably, this one is about 170 kilometres deep and won't contain any life at all. So this might be what I don't know what he's doing there. So this might be, if we were over here having a look at one of the inlets, maybe it might look a little bit like that, just out of interest. But there's unlikely to be any life, so he can go away. Unlikely to be any life of that size on Titan. It's just way too cold for that kind of thing to form. Now we'll go from here over to this part, and you'll see here a little island which wasn't there in the previous image and now is there. Now it's gone and now it's back. This is called, they call this the magic island or disappearing island. So one of the radar images from Cassini showed it there, another one showed it wasn't there, and it was seen again another time. The cause of that could be a couple of things. Maybe it could be a very low island and that tides are covering it every now and again. Or the most likely explanation seems to be bubbles coming up from underneath. So probably nitrogen bubbles of about 5 centimetres, so quite large bubbles of nitrogen gas coming up from the bottom, bubbling up on the surface. And for radar, the darker areas are where the radar, what if I shot this way, if a radar beam hits that and bounces away, you're not going to get any reading at all, so it'll look black. But if you have something rough, a radar beam will bounce right back to you again. So these areas are the rough areas, and so land and bubbly surface could look the same. And so that's why it's a bit unknown what that is. There have been other such things found on Titan since, but the liquid nitrogen seems to fit most of the models quite well, or the nitrogen gas bubbles coming up through. Now, we'll go down here to the Vidflumina river system. This is a methane river which is flowing into the sea at the moment, and it's sometimes called the Titan Nile, and the reason for that is this is the Nile on the left here on Earth, and this is Vidflumina on Titan. It's a different size, but if you expand it out, you can see kind of the similar shape and size, or similar shape, I should say, with a delta at the end where it reaches into the sea, and the river is kind of a similar shape. So you can see why they call it the Nile of Titan, even though it's a lot smaller. So, of course, a lot of these rivers are flowing in to the sea there, just like on Earth, but as I say, liquid methane, not liquid water. Now, Cassini also did a few microwave pings of some of the valleys as it was flying around this area. And so these are some of the areas it pinged with microwaves to see what the valleys and canyons might be like. So if we take an image of a canyon on Earth and just kind of squish it down a bit, it might give us an idea of what was seen. They found valleys, some of them up to, say, 600 metres deep. That's probably about the deepest, and with about 40 to 45 degree angles on the sides. And they were flooded at the bottom. So obviously valleys with liquid nitrogen rivers flowing through them. But the cliffs didn't seem to be the normal water ice. The reason being that liquid nitrogen can't dissolve frozen water ice. It can erode it, but it can dissolve frozen acetylene. So if these are made of mainly acetylene, which I mentioned before falls from the sky as well as a whole lot of other things, if these were piles of acetylene and other things mixed together, which formed over millions of years, it's quite possible that they were worn down by the methane rivers flowing through, just like we see on Earth. Possible also that it was just formed tectonically and broke apart, but it seems with the number of these valleys that that's probably the most likely, is that just like on Earth, the erosion has formed these valleys. And so you could do methane rafting on Titan if you like. You may have to paddle a bit because I'm not sure how fast that river is actually flowing, but it's something you could try if you wanted to. And that just gives a bit of an idea of, it's an artist's impression from NASA, I think that one was, just showing what Ligeia Mare might look like from the sky if you're looking down on it. And I think from what I can see, the shoreline here is that one over there, and this little river system here is what we're looking at here. So it's kind of just a fun little image to give you an idea of what you might see if you're high above the ground. Now let's have a look at Kraken Mare, which is the largest sea on Titan. And this again is a radar image of Kraken Mare. This one has a little bit less methane than Ligeia. As I mentioned before, a lot of the ethane from Ligeia Mare is probably flowing down into Kraken Mare, and so there's a bit more ethane in the sea than there was in Ligeia Mare, but also a fair bit of nitrogen as well. And that's 400 kilometres, so it gives you an idea of the size. It's a decent sized sea. Now here's just another another image, just shows what it might look like if we were looking out from an inlet on the edge of Kraken Mare. You would actually see the sea reaching and going over the horizon because Titan is fairly small, so curved enough that that sea would go over the horizon, so you'd be able to look at the sea and right over to the edge of the moon. So it's amazing to think that's on a moon in our solar system that you could, well, maybe it looks like that you can see with your telescope. We can, if we want to, have a tropical island holiday on Titan. There is an island in Kraken Mare up here. It's about the same size as the largest island of Hawaii. So this is made of insula, and when I say a tropical island, the only problems are that it's not at the equator, it's actually in the North Pole, and it's probably colder than we were when we originally landed. So it's the best Titan could do for an island, so that's our tropical island for tonight. So here's another computer-generated image. We can pretend that we're just travelling in our boat towards Maida Insula. You'll probably notice that it's very smooth, the sea there. The reason for that is the winds on Titan are very light breezes, so they wouldn't really give you many waves on the sea, maybe a couple of millimetres high. They might get a bit worse during seasonal changes, but when the radar images were taken, it was found that they were pretty smooth. There may even be some sort of oily substance on the surface, but we won't know that until we send something actually to these seas and have a closer look. So, of course, if you're at a tropical island, you want to go to the beach. So we'll go to the beach and we'll remember that it's still minus 180 degrees or so, so you will need a swimsuit, or actually not a swimsuit, you'll need a spacesuit. So we'll put our spacesuit on and then we'll head into the sea and go for a swim. And when you get in there, you'll just sink to the bottom. Now the reason for that is that liquid methane is much less dense than water, and of course we're made mainly of water, so we just sink to the bottom. So that's the end of the swimming. That was a bit of a failure. So here we are back up on the beach with our pina colada when we get caught in the rain. And there might be a bit of lightning there as well. Now of course, as usual, this will not be liquid water, this will be liquid methane rain. So this very cold rain will be pouring down, and we'll notice that the raindrops are quite large. Raindrops on Earth might get to maybe about 1/2 centimetre in diameter. The raindrops on Titan could be up to about the size of a grape, maybe 1 centimetre or so. They'll fall a lot slower because of the gravity. On Earth, rain would fall about 9 metres per second. On Titan, these big raindrops would be falling down at a fairly slow pace. You can feel each one landing on you as it hits you. So very large raindrops, and research or a bit of science has been done to work out what size raindrops we'd find on different planets and around the solar system, and so that's actually a scientifically found figure. That the rain on Titan can maybe every 30 years or so in the north and south, about 30 degrees latitude, can be fairly large rainfalls which could give up to, I think, about 30 centimetres of rain at a time. So a lot of flash flooding, methane flooding with those huge rainfalls, far and few between. But there is fairly regular lighter rainfall. This is a picture of a rainbow on Earth. And you may know that a rainbow on Earth has not only got the visible colours but also infrared and an ultraviolet component. On Titan, it's thought that there may be rainbows, of course, when it rains. You wouldn't be able to see the visible light because visible light doesn't travel very well through the atmosphere there, but there may be infrared rainbows. So if you had your infrared goggles, you may be able to stand in the rainstorms there and see some infrared rainbows as well. So while we're talking about rain, clearly Titan has a methane cycle just like Earth has a water cycle. So methane evaporates into the atmosphere, forms clouds, maybe about 8 to 20 kilometres up in the sky. It'll rain methane into our methane rivers, and the cycle will keep repeating. A little bit of ethane sometimes mixed in with that rain as well. Another weird thing on Titan is there is a little bit of drizzle or rain with no clouds occasionally. And so that would be like us going out on a clear day and getting rained on for no apparent reason. So it would mainly be just the methane forming droplets out of the atmosphere. Now the reason they know that's the case is that Cassini found a few patches which were obviously dry on one pass and then came past again. There'd been no clouds, but then the ground was seen to be wet. So the best explanation was rain falling from the sky without clouds. So it's kind of a weird thing we'd find on Titan. Now, while we've been looking at all these seas and lakes on the surface, we may have forgotten about the fact that there is a saltwater ocean only 80 kilometres away from us. So if we go down under the surface, we'll find that there's an outer ice shell of 80 kilometres deep, roughly about 80 kilometres deep of normal ice. Below there is an ocean, which may be 300 kilometres deep. That'll be a very salty ocean, maybe as salty as the Dead Sea on Earth, maybe about 30% salt, and also a bit of ammonia in there as well. Now that will, obviously the salts and the ammonia will help it to stay liquid, so it might be a little bit slushy, but definitely is a global ocean there. Below the ocean is another layer of ice. It's a high pressure ice called ice 6, and that's a high pressure ice which has a greater density than water, and so that stays at the bottom of the sea with the normal ice at the top, and that's all sitting on top of the rocky core. And as I mentioned at the start, that means that little Titan here could have 10 times, or maybe even more than 10 times as much water as all of the Earth's oceans put together. So that's a huge amount of liquid water. It's really quite incredible. That little place has all these kind of records, solar system records. Before we head back to Earth, we should just have a quick look at the south pole of Titan as well. So for the last couple of slides, we'll just head back down to the south pole and we'll have a look at this place here, which is Ontario Lacus. This is a southern lake on Titan, which is called Ontario Lacus because it's meant to be roughly the shape of Lake Ontario on Earth. It's kind of more like a footprint. Looks like a big footprint there with a heel there. Now that, as you'll notice, has got a lot less methane than the northern seas and a lot more ethane. The reason for that is this red line here shows what was probably an old shoreline, or maybe a fairly recent shoreline, but clearly the sea has evaporated and left a lot of the ethane behind, so the methane has mainly evaporated. So it is a bit like the Dead Sea on Earth with salt water and fresh water, whereas this is methane and ethane again. So this lake may have almost be given the name of a sea if it had been larger, and may actually fill up again as the methane evaporates from the north and heads down to the south. But I think we have to kind of watch Titan a bit longer to see what happens with the spreading of methane from one pole to the other. Now, NASA have just have a little bit of a short video here which kind of shows Ontario Lacus, what it would look like if you were to fly around it. So I haven't got the sound here, but I'll just commentate on what they would be saying. So that's Ontario Lacus there, just near the South Pole. And if we zoom in, you can see it's coloured black, and they think it might actually be black, possibly. So we head down to the surface here, and you can see the hills here, the ice mountains, which have been exaggerated in height just so you can get an idea of what these hills and mountains are. And then we're flying around this coastline here where we can see a bit of a long, smooth beach, which shows that there's been a bit of a change in the levels of the sea there, or the lake. And heading down here, there's an inlet here which I think is fairly recent. So it's a little bay that's been formed over here. Then we head back across the sea. And if we look over in the distance here, we can see a river here. And based on this delta here where the river is flowing into the lake here, it's pretty certain that's a very slow-moving river and a very shallow sea or lake. So that's probably only about 50 metres deep. The deepest sea or lake on Titan was Krakenmare, which we saw earlier, and that was about 300 metres deep. So it doesn't sound very deep, but 300 metres is a long way to go if you're going to sink under the lake or the sea. And just as we head back, we can take off through the atmosphere and fly through this very beautiful hydrogen cyanide and benzene cloud. This is a photo of of this cloud in the southern hemisphere of Titan. It's about 1 million square kilometres, so it's a pretty large cloud, and about 150 to 200 kilometres up in the atmosphere. So heading through that would be fun. You just wouldn't want to breathe in too much. Well, nowhere on Titan would you want to breathe at all, but even less so here with the hydrogen cyanide and ethane. So that means we can leave Titan now and head back to Earth, and I'll just give you a bit of colour here after all that orange and yellow and brown. It's a bit hard on the eyes, and so there's something a bit nice to look at for a moment. So just before I finish off, we'll just have a look at those main points. So we know that Titan is very cold, minus 179 degrees Celsius at the warmest, possibly down to minus 181, minus 182 up in the northern parts. It has methane seas, lakes and rivers, and methane rain. We saw the electric snow and the electric sand dunes, the ice mountains. We saw it had that immense atmosphere, much, much higher than Earth's atmosphere, and that substantial subsurface ocean. So that's a few things. There's probably other things we could look at some other time, but that's probably enough for tonight. So I'll leave you with that to finish off. So if anyone's got any questions, you're welcome to ask them.
So
Yeah.
basically it would smell really, really bad.
What was that?
It would smell bad.
Well, that's interesting. I don't know. Well, you probably wouldn't smell it because your nose would be frozen off. But if it did have a smell, I think methane that we have on Earth, I think they actually give it an odour, a bit of an odour. So I'm not sure what it would smell like, but It would be interesting, actually, yeah. One thing some people have asked is what would happen if you throw a match into one of those seas. But I think you'd probably find, well, first of all, the match would just be frozen solid, but also there's no oxygen as well. So I think you'd need oxygen to ignite them. I don't know what happened if you crashed a spaceship into it and it was burning, but it'd probably be so cold that it would probably put the fire out, the flames out pretty quick. Yeah.
So do you think the lightning might be able to spark the methane?
No, I think that there's been no sign of any fire or anything there. So lightning.
Anything to spark a fire, like an asteroid or?
Well, the best an asteroid could do and has done is created a few craters and melted the ice so that there were liquid water lakes on the surface in the past. And
No explosion. Is there any evidence of
not a fiery explosion, no, just a very energetic impact which formed a crater. One of them is called South Crater, and that's where that Dragonfly mission is going to go to in the 2030s. And it's going to fly out there and see what kind of molecules might have formed.
Yeah, but fire needs oxygen, right?
Oh yes, yeah. So yeah, not going to have any fire there. It's just going to be pretty safe.
Yeah, I got that part.
Yeah, that's all good. No worries.
Wouldn't the rain turn to hail if it was frozen?
So the methane itself is still liquid down to about minus 183. So it's near the triple point. So like on Earth, we have frozen water, liquid water, and water vapour. And that's because we kind of got that triple point where the pressure and temperature are just such that just little changes here and there can change those states. And it's similar with the methane on Titan. So methane is kind of the analogue to water on there. So good question though, because up in some of the higher mountains there may be a little bit of methane snow on top as well. So that's possible as well. Probably some ethane snow as well. I think there's some ethane clouds as well. Yeah.
I'm curious why such a small planet, moon, has such a thick atmosphere.
I know, it's amazing. Part of it will be because the...
So cold that it just condense out.
Yeah. Part of it is because the gravity is so low it can spread out a bit further. And also a lot of it won't escape because it's cold. The molecules don't have that kinetic energy, so they won't fly off as easily. So the escape velocity, the molecules wouldn't quite reach that escape velocity. Having said that, Titan sometimes does go out of the magnetosheath, and of Saturn, and so the solar winds actually do at times form a bit of a methane or gaseous tail from it at short time. So it is losing a bit, possibly replenishing some of that methane from maybe cryovolcanoes. There might be some of the ammonia from the sea below might be coming up through and replacing some of the nitrogen, and there may be some methane pockets as well. So a lot happening there that we still don't know, but that's a good question, yeah.
You said when Titan exits Saturn's magnetosphere that the methane trails out. Does that mean that Titan does not produce a magnetosphere for itself?
That's exactly right. So Titan doesn't have a magnetosphere, and also because it is travelling through Saturn's magnetosphere at a constant distance, and the magnetosphere of Saturn is aligned with Saturn's rotation. So as Titan orbits, it doesn't change how the magnetosphere affects it. So that means there's nothing to cause what they call a secondary magnetic field. The reason I'm saying that is over at Jupiter, Europa is a moon with a saltwater ocean as well. And Jupiter's magnetic field, I should say, is tilted. So as Europa goes through that, it's going through different strengths of the magnetosphere, and that causes currents in the ocean of Europa, which then gives an induced magnetosphere, or magnetic field, I should say, in Europa. So Europa does, but that's the reason Titan doesn't. So, good question. Now, someone else had a question? Oh, over.
With the atmosphere being so much higher, but the gravity being so much less, what are the thoughts around being able to take a ship and leave the planet?
Probably wouldn't be too hard, I don't think. Yeah, I think, but yeah, because the gravity is so low, I think it'd be quite easy to take off through that atmosphere. Yeah.
Just have to go a lot further, so you probably use similar fuel.
Yeah, I guess, yeah, you're kind of thinking from the friction, are you, as you're going through? So the friction of the air would kind of have a little bit to do with it, but as you got further and further up, the atmosphere gets more tenuous, so yeah, wouldn't be too bad, yeah.
Yeah, and wouldn't Saturn's magnetic field be pulling against the spacecraft?
The magnetic field wouldn't be, though, yeah, the gravitational field would. So the distance, though, from Saturn to Titan, I don't think the escape velocity would be too bad for a spaceship taking off. And I think even at Saturn it wouldn't be too bad as well. But it'd take a bit more effort, yeah, a bit more fuel and thrust. Yeah.
You touched a little bit on it earlier, that there being only like light winds and barely constant temperatures. So given that it's so far away from the sun, I guess there's not these like big temperature gradients like on Earth to drive like big.
That's right. Yeah.
So is there any indication that there being like some weather systems, or is it basically just?
Not too much of a weather system. There is thoughts that that there may be a system that kind of goes from the south to the north and the north to the south. So that's why they thought the methane might evaporate, and eventually those large seas at the top might kind of evaporate, end up at the south. So there may be kind of a cycle kind of from north to south. But yeah, kind of, you know, rather than on Earth where it kind of goes that way. Although we have got those kind of breezes going around Titan as well.
Sand dune formation, I mean, you said it was more like snow, but that's wind.
Yeah, so that is wind driven. So there's occasional winds that they think from changes in season. So there are little bits and pieces of winds that will drive the formation of those sand dunes. Yeah.
How would you get through the challenge of having your spaceship just blow up once you kind of created like a fire? Like, you know, like a...
Oh, you mean if you had a malfunction or something?
Fuel. Well, if you had fuel, like, don't you, like, I don't know exactly what happens in space, but don't you get like oxygen, and you use that to kind of like yeah,
they kind of carry their salt. Well, depending on the type of rocketry.
Wouldn't it blow up because of the methane in the atmosphere, or no?
I guess if you had oxygen and could somehow get the methane in, if you had a malfunction, you might have a bit of a problem.
But if you created thrust with a, like, you know how they do it on Earth, wouldn't you just blow up the whole spaceship?
No, because it's generally pushing out the exhaust away from the spaceship anyway, so you'd be pretty safe. Although the Huygens lander just came down with a parachute, so I guess if Elon Musk had one of his landing, ships that could land vertically, take off again.
Like, I know landing is very easy, but taking off.
Yeah. Oh no, you'd still be pretty safe, I think. Yeah,
you think you would be able to take off?
Yeah, you could take off. Yeah. Just with a good, powerful spaceship. And of course, the gravity is only 1/7 of the Earth, so it's not too hard to sort of fight through that.
But it'd be kind of like taking off on the moon, right? Because the moon is like
pretty much, yeah. That's right. It's kind of fairly similar gravity to the moon as well. Right, no other questions? Nothing online today? I must have answered them all.
Well,
Great, thank you.
Very much.
This case, and equally every time you present it, it's just a little bit of a different twist to it. And
Yeah. As I learn new things as I go.
I really feel like we've been to Titan tonight.
Oh, that's good.
Thank you very much indeed. Thank you.